So for this one, we are going to move or walk 6.8 kilometers in a direction of 43.3 degrees north of east. That's what this means here, north of east. Okay. Then after that, we're going to go 6.3 kilometers due north. And after we've done those two walking paths, we're going to figure out how far we are from our starting point. So what is our displacement in the end from our starting point? Okay, so to solve this problem, the first thing we want to do is pick a starting point. Here I've picked this starting point here. This is where I'm going to go for my first vector. And I like to draw a little X here and then tell myself that north is up, south is down here, here's east, here's west. Okay, now our first direction is some distance at some angle north of east. Here is east, and I'm going to go at some angle north of that. So my first displacement vector is going to go off like this, okay? And this angle right here is going to be that 43.3 degrees, okay? This is my angle north of east, okay? And this has a length of 6.8 kilometers. And then from there, I'm going to draw in another little X, north, south, east, west. And then from here, I'm going to go 6.3 kilometers due north. So I'm going to go just up here, okay? And that's 6.3 kilometers, okay? Now, I know these vectors are not to scale. I'm just drawing them here to give us some sort of sense of direction. Okay, and so our total displacement then will be the vector that starts at the tail of this vector down here and goes all the way up to the head of this vector right here. This is my displacement vector. That is D. That's what we're trying to solve for. Okay, now I know this is a big, kind of complicated drawing here, but we're going to work through how we're going to solve this mathematically. Okay, now let's see. So the first thing I want to do, I'm going to call this vector right here, I'm going to call this vector A. And I'm going to call this vertical vector, vector B. So just like how we did the previous PreLab problem where we found the magnitude of the sum of two vectors, we're essentially going to find the magnitude of the sum of two vectors. That's our displacement magnitude here, okay? So, first, let's find the components of my first vector, my A vector, okay? So it's going to be AX, X hat, plus AY, Y hat. Okay, let's find the X and Y components. If I go over here, here's my angle, here's my vector. I can make a little right angle triangle right here. Okay, here's my right angle. The hypotenuse is my 6.8 kilometers, magnitude of vector A. This leg of that triangle is my Y component of the A vector. This leg of this triangle is the X component of my vector A here, okay? So we know that this angle is 43.3 degrees. We're going to invoke our trigonometric identities. So this is my angle. I'll call this angle theta. So the angle, let's see, let's go sine theta is equal to, sine is opposite over hypotenuse, so that's equal to AY, the Y component of my A vector, over the magnitude of my A vector. That's our 6.8 kilometers. So AY is equal to the magnitude of A sine theta, okay? And then similarly, we can do this for to figure out how to calculate the X component of my A vector. We use cosine for that. Cosine theta is equal to adjacent side, that's my X component, divided by the magnitude of A. So AX is equal to A magnitude cosine theta. Okay, so the magnitude of my A vector, that's 6.8 kilometers times sine of 43.3 degrees. So my A component of my, or Y component of my A vector then is 4.66 kilometers, okay? And then the magnitude of A here for my X component, that's also 6.8 kilometers, cosine of 43.3 degrees this time, and then my AX component is 4.95 kilometers, okay? So I can plug those in into my A vector up here. So A vector looks like 4.95 kilometers in the X direction plus 4.66 kilometers in the Y direction. Okay. And now my B vector is actually a lot easier. Okay. B vector, it's vertical. It does not have an X component. So BX component is 0. Okay. BY, though, is non-zero. And since the this entire vector is only in the Y component, so BY is going to be the full 6.3 kilometers. So my B vector just looks like 6.3 kilometers in the Y hat direction, okay? So then we want the magnitude of the sum of these vectors, which would then be the total displacement, this D vector here, okay? So I called it D. Yes, I called it D here. So sometimes I call these the resultant vector. If you ever hear me say a resultant vector, that's the same thing as what I'm working with right here. So the magnitude of this vector is going to be the sum of the X component of my A vector plus the X component of my B vector plus the sum of the Y component of my A vector plus the Y component of my B vector, okay? So then we've got AX, which is 4.93 kilometers, plus there is no BX. So the X component of my displacement vector is just 4.95 kilometers because this BX term here, that's 0. There's no X component of my B vector, okay? And then I've got my component AY, which is the 4.66 kilometers, plus the component BY, which is 6.3 kilometers. The sum of those is 11 kilometers, and that's in the Y hat direction. Oh, I've got to put my vectors here. Okay, so that's what my displacement vector looks like in vector form with its X and Y components. So that makes sense. We go over 4.93 kilometers, and then we go up 11 kilometers. That's our total displacement vector here. Now for the magnitude, we use Pythagorean theorem. The magnitude of this vector is going to be the square root of dx squared plus dy squared. If we call this component dy, and if we call this component here dx, okay? And so that's going to be equal to the square root of 4.95 kilometers squared plus 11 kilometers squared, okay? And if we take that, then we find that the magnitude of our displacement is 12.1 kilometers. So that's what we're looking for, okay? Now, whenever you solve this problem, you will be going north of east, and then you will be going directly north, but the value for your angle here is going to be different than what I have, and the value for both of these displacements here is going to be different from the numbers that I have here as well.